Hello friends, I am Sunny Patel and I am going to introduce altruistic scheduling in multi-resource cluster with my friend Abdul Rashid. The paper was originally published by Robert Grander, Mushraf Chaudhary, Aditya Akela and Ganesh Anant Narayan. So what is the motivation behind this idea? Well, first of all, let's understand what do we mean by altruistic scheduling. Altruistic scheduling means jobs give up resources assigned to them temporarily so they can be used to finish other jobs. The problem with the current schedulers is that they follow greedy approach when it comes to resource allocation. We know that greedy approach always gives short-term optimization and sometimes lack to provide overall optimal solution. This problem is inherited here as well. Most of the schedulers try to optimize their priority objectives and often neglect secondary objectives. Thus, the overall performance of system does not get optimal. To solve this problem, authors have introduced a novel system known as Carbine, which takes altruistic approach in which jobs tends to relinquish resources so other jobs can be finished quickly. This figure is an example about issue we discussed earlier. In figure A, we can see that there are two jobs J1 and J2 and there are three stages S0, S1 and S2. Stages required for job J1 are shown in orange, whereas stages required for job J2 are shown in blue. There are also dependencies for job J1 which is shown by arrows. Now let's consider that both jobs arrive at same time. Now traditional scheduler, as shown in figure B, schedules the tasks of both jobs in their fair allocation. It means it allocates available resource capacity equally between both jobs. Figure C shows allocation done by an altruistic approach. Now what is the difference between both images? Well, as we can see that in figure C, job 1 gives up some of its resources so that job 2 can finish its execution first. After that, job 1 finishes normally. So what advantage do we get from this type of scheduling? Well, if we calculate average job completion time, then the traditional scheduler we get 2.05 time units, whereas for altruistic scheduler we get 1.55 time units. Well, why? So in previous figure, in figure A, we can see that job 2 runs for 2 time units, whereas in figure B, job 2 runs for only 1 time unit. Thus, altruistic approach gives better average job completion time. Now the question is how to determine which resources can be considered as leftover and used for altruistic scheduling. To answer this question, authors share their research. After computing the fraction of allocated compute, memory, disk in and disk out, and network in and out bandwidths that could have been allocated without affecting any job completion time at Microsoft's production trace, 50% of the time, at least 20% of the allocated resources for the resources listed above could be used as leftover and scheduled via altruistic scheduling. Microsoft Production Trace is the trace of storage workloads of production servers taken by Microsoft to support research work. This slide shows some properties that matter most in order to achieve altruism. So the first is total number of stages that a job can have. Second is number of stages of with multiple parents. Third is the length of critical path of directed acyclic graph, which shows the dependencies between the jobs. And the fourth is disjoint paths of the directed acyclic graph. Now let's see how this approach can be realized. So this slide shows the objective. Given a collection of jobs along with information about individual tasks, expected multi-resource requirements, durations, and directed acyclic graph, which uh, they must be scheduled such that each job receives a fair share of cluster resources. Jobs complete as fast as possible, and the schedule is work conserving. All information about individual jobs are unknown prior to their arrival. In short, the main goal is to achieve fair allocation, short job completion time, and short overall time, also known as total time, to finish a set of jobs. There are two types of scheduling: offline scheduling and online scheduling. Offline scheduling In offline scheduling, the scheduling decisions are made prior to running the system, while in online scheduling, scheduling decisions are made on runtime. Offline scheduling of a job set given a directed acyclic graph for objectives like resource fairness, performance, and efficiency is an NP-complete problem. The desired properties for such scheduling are: first, fast completion, which means each directed acyclic graph should be completed as fast as possible. Work conservation, meaning available resources should not remain unused. Starvation freedom, which means no directed acyclic graph should starve for arbitrarily long period of time. Offline altruistic scheduling. The cluster schedulers typically operate in two phases. One is interjob scheduling, which means scheduling between jobs. Another one is intra-job scheduling, which means scheduling of tasks inside same job. This happens because, as I already said, in offline case, the dependencies and resource requirements are already known and does not change while job is being executed. Increasing leftover via inter-job scheduling. The modern clusters are shared between many groups and users. Therefore, the main goal of production cluster becomes performance isolation or multiple resource fairness. It means if multiple users are accessing the shared cluster system, our goal is to provide an illusion such that it seems to a user that he or she is alone accessing the system. To accomplish this, authors use fair schedulers in design of carbine system. The reason behind it is single or multi-resource fair scheduler enforces resource sharing between all running jobs. It elongates individual job completion times the most compared to schedulers focused on other primary objectives. Also, fair schedulers provide the most opportunities for altruistic scheduling. Determining leftover for individual jobs. Now, Carbine's intra-job scheduler aims to maximize the amount of leftover resources from each job. To ensure this, only those tasks are scheduled which must start running for job K to finish it within time duration T of K, and its rest of the resources are altruistically given up so that if there are other jobs which require those resources can continue their execution. Computing this is simple. A reverse or backward packing of tasks from Tk to the current time. Packing tasks in time as close to Tk as possible, potentially leaving more resource available at earlier times. Let's understand this by an example. In this figure, we can see that S2 can only start execution after 2 time units or more accurately, it can start execution after S0 and S1 has finished. This can be understood by this figure. Here we can see that for job J1, S2 has dependency over S0 and S1. Now since S1 can be finished before 2 time units, we can postpone execution of S0 and release resources so that job J2, which doesn't have any dependencies and only one stage, can finish the execution. So as we can see here, Carbine can postpone both tasks from S0 and one task from S1 until at least the first time unit, donating 0.29 units to leftover resources for S0's tasks and 0.21 time units for S1's task. Similarly, job J2 donates 0.21 units to leftover resources, making it a sum of zero point 0.5 leftover resource units. Redistribution via leftover scheduling. The leftover scheduling has two main goals. First is minimizing the average job completion time by scheduling tasks from jobs that are closest to completion using shortest remaining time first or SRTF. The second objective is maximizing efficiency by packing as many unscheduled tasks as possible. Now let's see some properties of offline scheduler. The first one is the former action of the leftover scheduler enables fast job completions, while the later improves work conservation. At the same time, because the intra-job scheduler ensures that P of k values are not inflated, the overall scheduling solution maintains the fairness characteristics of DRF and provides same performance isolation and starvation freedom. Thus, Carbine scheduler satisfies all the desirable properties. Now, let's see how clusters are designed in proposed system. So, there are several points that needs to be considered while designing clusters. The first one is the data locality, which says that execution should be performed where the data is located. The disk and memory locality significantly improves this aspect. According to authors, delay scheduling says that waiting for even a small amount of time significantly improves data locality, and thus proposed system is likely to find data locality when it is eventually scheduled. The second important point is straggler mitigation, which says that overall performance can be affected by some nodes which are running slow due to some reason. According to authors, Carbine system is likely to prioritize speculative tasks during leftover scheduling because it selects jobs in the SRTF, which is also known as shortest runtime first order. The third important point is hand- handling tasks failures. Carbine, just like existing solutions, does not distinguish between new and restarted tasks. In case of task failure, Carbine needs to recalculate the completion estimate of the corresponding job. Now onwards, my friend Abdul will discuss further about design aspects and will also explain the implementation. Thank you.
Hello, my name is Abdul Wasa Rashid and I will be continuing from here. Thanks, Sunny. So, now how to enable altruism in cluster schedulers? There are two important components that are required. First one is a local altruistic resource management module, and the other one is leftover resource management. The altruistic resource management module is present in each application, and its job is to determine how much resources the applications can yield. Second one is implemented by the global cluster scheduler. This module is called the leftover resource management, and this module just relocates the yielder resources from all applications. Now, the RPC mechanism. The RPC is short for remote procedure call, and these are expanded so that the new information between the two schedulers are propagated between one another. So, how are these implemented and on which level are they implemented? Well, for monolithic schedulers such as Yarn, the altruism module is implemented by the individual job managers like the Spark or the test masters, and the leftover management module is implemented in the cluster wide resource manager. And for the two level schedulers such as Mesos, the global allocation module is managed by the leftover resource management, whereas the altruistic module can be implemented at the frame level such as Spark and MPI. These architectural principles are similar for shared state schedulers such as Omega. Carbine system. We have here a carbine system figure that the authors have used. In this figure, it is described how the authors implemented the two modules to provide altruism. The core pieces of a typical parallel cluster schedulers is illustrated, and the new functionality is added to integrate Carbine as shown in orange. Literally, the authors added about 1400 lines of code to Yarn just to implement Carbine. In today's data parallel cluster, the schedulers divide the scheduling process into three parts. The first part is the node manager, the second part is the job manager or the application master, and the third part is the cluster wide resource manager. Each part is explained briefly as to what they entail. The node manager is responsible for running tasks and reporting available resources. The node manager is present on every machine in the cluster. Node manager communicates with managed servers and administration servers using two-way SSL to verify the identity of server instances that it communicates with. You cannot use node manager with an unsecured communication protocol. The next one is job manager or application master. This runs on some machines in the cluster and holds job context information such as whether the job is completed or is it in process or is it pending. It also holds the information of dependencies and the resource requirements like how much memory is required, number of processors required, etc. The last one is cluster-wide resource manager. Here, ask requests are received from various application masters for their pending tasks to be scheduled, and information is also received about the available resources on different machines from node managers through heartbeat messages. Basically, the resource manager receives requests with the above said information, and depending on this information and fairness, it assigns tasks to machines. An ask contains information such as preferences for data locality, the amount of resources required, and priorities at which tasks should be executed. Priority is an useful mechanism to enable application managers to encode their preferences to execute one task over the other. Example like ordering in the DAG or failures. Implementation. So now about the actual Carbine implementation. Carbine is built as an extension on Yarn and test frameworks. There were some modifications done so that the pseudocode could be implemented. The following modifications were made first in the RPC mechanism, second in the test job manager, and the third in Yarn's resource manager. In RPC mechanism, the remote procedure call protocol is modified in the RPC mechanism. It is enhanced between the Yarn resource manager and the test application master to propagate the total resource allocation of a job as computed at the resource manager according to the fairness policy enforced in the cluster and the current runnable jobs. And the other modification here is the ask data structures. It is extended to support different type of ask requests such as ask default and ask altruistic. Ask default is for tasks that it must run in order to not be slowed down due to altruism, and ask altruistic is for tasks that it may run if the scheduler tries to use all the allocated resources. In test job manager, the most recent resource allocation for a job received from the resource manager, the Carbine enabled test application master altruistically schedules the remaining unscheduled tasks and their dependencies. The intra-job scheduler is implemented to include resource requests for tasks that should be scheduled via altruism. These are the ask default requests. It also computes the ask altruistic using default intra-job scheduler in test that decides on a breadth first ordering for scheduled tasks. The scheduling process, Yarn resource manager is triggered when a node manager reports available resources. The Yarn's resource managers matchmaking logic was updated to project tasks resource requests onto available capacity. First, among the runnable jobs, it computes periodically their DRF allocation and propagates the corresponding resource allocation on the next heartbeat response to every application master. Second, it schedules tasks requests from jobs, asks default using similar heuristics to do packing and reduce job completion time. Evaluation. Carbine was evaluated on a 100 machine cluster using publicly available benchmarks, the TPCDS, TPCH, and Big Bench, as well as Hive traces collected from large production clusters at Microsoft and Facebook. One of the key findings was Carbine can closely approximate DRF, Tetris, and SJF in terms of fairness, efficiency, and performance respectively. in both offline and online scenarios, and it provides 1.26 times better efficiency and 1.5 times lower average completion time than DRF. Experimental setup is as follows. The workloads, as told earlier, are a mix of jobs from public benchmarks and from Microsoft and Facebook. Microsoft workload has 30,000 job DAGs with millions of tasks, and Facebook workload has 7,000 jobs and 650,000 tasks spanning 6 hours. The cluster uses 100 bare metal servers. Each machine has 20 cores, 128 GB of memory, 128 GB SSD, a 10 GB network interface card, and runs CentOS 7, meaning the cluster can run up to uh, 2000 tasks in parallel without any congestion. To run Carbine at a larger scale, a simulator was built that replace job traces and to gain more insights into Carbine's performance. This simulator mimicked various aspects of the logs, handling jobs with different arrival times and dependencies, as well as multiple fairness and scheduling schemes. Now about the performance. The primary metric to measure the performance is the average job completion time, JCT. The average job completion time is computed as the duration of an approach over a duration of Carbine. If this is greater than 1, then it means that Carbine is performing efficiently. Additionally, make span is also used here. Make span means it's the total length of the schedule when all the jobs are completed. It's done to measure the efficiency. To measure fairness, Jane's fairness index on 60 seconds time window intervals are computed. The authors plotted the average, minimum and maximum values until the workload completes. Uh, this is the Jane's fairness equation. Here xi is the amount of resources given to the ith job, and here 1 is the best case and 1 over n is the worst case. Now let us compare performance, efficiency and fairness in the offline case first. Uh, in terms of fairness, DRF approach is the most fair approach with a fairness index of 0.86 on average. Carbine is almost as same as the DRF approach. The difference is just 0.05 units, whereas Tetris is 0.12 units and SGF is 0.22 units away. Carbine is unfair on small time intervals due to resource allocation. On longer time intervals, it is almost the same as DRF. Comparing the job completion time, SGF is the most improved with Carbine only 1.06 times the worst average job completion time. This is because Carbine performs shortest remaining time first, SRTF in short, during allocation. Tetris and DRF are 1.46 and 1.59 times on average respectively. Now comparing efficiency, Tetris is the most efficient mainly because it efficiently packs all the tasks across jobs. Here too Carbine is the closest scheme, which is only 1.03 times worse than Tetris. In comparison, DRF and SGF are off by 1.26 times and 1.43 times respectively. Now in the online case, where jobs arrive over time, Carbine closely matches DRF in terms of fairness, with just 0.06 units worse. It closely matches SGF with 1.2 times worse in terms of performance, and it closely matches Tetris with 1.07 times worse in terms of efficiency. Here the margins are slightly larger when compared to offline case. Conclusion. In conclusion, modern cluster schedulers focus on performance isolation through instantaneous fairness while relegating performance and efficiency as secondary goals. The users only perceive or discern of isolation after the jobs are completed. And as long as the job completion time remains constant or does not change, a long-term altruistic approach such as Carbine can be used instead of an instantaneous one without inflating their completion times. With the combining of the leftover resources, and Carbine improves the application level performance and cluster utilization significantly, and it provides the same level of performance isolation as modern schedulers. The isolation is not affected. This paper by the authors introduces a new approach for job scheduling, where they consider efficiency of the jobs as the main criteria in designing this approach. The job completion time was decreased significantly while keeping fairness in resource allocation. Not only the idea by the authors was groundbreaking, they also realized it by implementing this approach on simulators to achieve the goal. Here the goal by the authors is not to bring out the best approach in practicality, but to do better as much as possible in every domain. From the graphs, the jobs that were executed on simulators, it was evident that Carbine is not the best in any single domain, but the overall performance is better than any other competitor. So we can conclude that the authors have achieved their goal with the introduction of a new efficient approach. With this, I like to end my presentation. Thank you all.